we're starting with Ramses Mena from UNAM in Mexico, who will tell us about continuous BNP processes.
Thank you. Oh, I don't need this one. Well, thank you very much for the invitation. Thank you for organizing this. It's a great initiative. I think we could, use the process. And then I think the thing Steven in my head is a very simple paper, very easy to read. We are so much complicated. We are comparing with all the methods around. What would have this impact in our community? So that is something to reflect on when we write papers. So what we're going to speak about today is something that it's a lot of story goes back to when I did my PhD and then carry on in a kind of agenda of my research somehow. And at the time when I finished the PhD, 2004, 2003, I met Steve in a conference still in Denmark, and we were talking about the dependent dirichlet process. But I wasn't able to understand him very well. So he made interest for a good time, so I don't know, but it was boresome. So, and Steven Nacional plans for all foreigners, different groups. And well, this way is super easy, right? So, this is the when I was right. Anyhow, so it's not working this either.
Is that working?
It's not working, no. So you put a particular way of presenting.
Because it's you have to click after it's on Zoom.
It's on Zoom. Okay. So I click this one, right?
Yes.
Okay. So there's a very nice to the so he's not always going to stronger abuse. That's what I think the picture all the time. So but I was thinking about as I said today, and we have to wait, let's come put this on. We have it, you just put like normal. So I have to be very close, I think. So suppose we observe the following here. So one thing we do is immediately we know the histogram, and then we as a statistician use the normal distribution is not very good. We are basically parametric guys, so we model through most mixed models. And we know how to do that, and we're going to work with the text, it's a conference based on parametrics. But what happens if you have more information about the time axis, and you know that there is a covariance, something that is indexing this observation that you're looking at. In this case, it's time, and it's the central point of the topic is around this. So essentially, we have this kind of models, and these models are very nice. We know how to apply them. We have many techniques we can solve for them. If we know a bit more about the data, for instance, if we know the data continuous time, the nature of the phenomena that we are observing evolves in continuous time, although the data will share in discrete time. But then we have these models, right? The feature processes, so many models for continuous time. The problem that most of the models we find in the literature is that they are parametric. I mean, it's a problem, a big issue to actually apply in real statistical sort of way. I'm not going to go into it. But what the idea of Steve, I always mess up this now. So the idea of Steve, it goes into how to model this kind of behavior without actually this assumption, these assumptions of the parameters. For instance, in this diffusion process, the parameter and the variance or the probability have a particular form, and they are already assuming a model, right? Which is not particularly probably best for the data. So of course, there are plenty of different data and plenty of different marginal distributions. Like for instance, we have here something that might be continuous time, continuous to the space. Here something that is continuous, discrete, something that is continuous and discrete also in many words. So we have different marginal distributions. And then something that pushed forward my research at the beginning of my PhD long time ago, with Stephen Walker, was to model this kind of thing. So we have more complicated stuff. We heard in the talks moment that the covariance can be many things. So you might have some higher dimensional problems, and you might have more of one trajectories, and have more data at given time to actually estimate them, to feed your model, and to have their statistical model. Or you have something that might not even be an Euclidean space, something like that. So they have conflicts in this kind of story. So there are many approaches if you go to the literature of statistics and stochastic processes. One is to model your stochastic equations. You say a stochastic equation to all the dynamics of thing or the data you're modeling through continuous time model. And when you find the direct specification of the law of this function that is evolved in continuous time. So the second one is a bit more vague, right? So, and if you look at the parametric point of view, this might sound easier, because we have an easier way to fix it. But the other one is a bit vague. So we're going to speak about those two. But something we're going to look at is case structure of macroeconomic dependence, because it's a way to simplify things. If you look at the whole dimensional, kind of dimensional distribution, you can go down, so you can go, but it's too much. So you have to sort of limit yourself a bit, and a way to do that is to macroeconomic. So I think we all agree that symmetry stability are fundamental for statistical inference. As Bayesians, we know that stochastic symmetries like stability allow us to learn about the phenomena that we are modeling in time. So major symmetries that we look at are independent, electrical distributed, stability, and stationary. So invariantness of this symmetry when we look at is important. We do inference and we do predictions to that. We are really good, given the method that we're going to see the workshop after. We have this article kind of condition predict this same symmetry as well. Essentially, we choose a model approach to have a trade-off between distributional flexibility and stochastic dependence. Of course, you may have a very easy model with a with very easy, like ARM models with linear, very easy dependence, but with a very flexible distribution. Or the other way around, we have a very complicated distribution, sort of a very complicated dependence with an easy distribution. But that's what happens with another model, right? You have a way to sort of transform that. So the idea that you have a model, in most of the things we use as processes, transform this is something that we can study easily. And we know that, for instance, you have certain series and they transform it to something stationary in order to do estimation properly and to do it. So the marginal behavior in all this is a key point when you do this kind of studies. And that's what we're going to look at into this area. So we need to be better to actually start from a stationary point of view. So we have that model, those data that we saw at the beginning. You need to say they are not stationary, because we are used to think about the stationary process as something that goes along very nicely when you invariant manual distribution. Well, we have this from parameters, you know that the distribution might have many flavors, many modes, and the stationarity might have this uptime behavior results. So that's the idea of the story, and it goes back to part of the thing that was in PhD, and then when I spoke with Steve, in that conference, he was telling about that I remember. So the ingredients for this talk are 6 idea and stochastic symmetries. So I will speak about these 3 points, and I will see if the time is enough. So the first thing is that the idea of marginality comes from stability, the concept that we may first know, and then we go to the idea of continuous time dependent. Right, this is easy after the talks this morning, and then a different idea covers it. So first, macroeconomic processes are continuous time, in this case, continuous time processes that evolve in time. And when we talk about stationarity, strict stationarity, we are saying that there is an invariant measure that preserves through the transition. So the transition density or transition probability we use for this if this invariant measure invariant. So this measure invariant. So this is an example. You have this data and you have invariant measure. So this is the whole idea. So the idea is how to construct models that keep this very general. But this red distribution can be a general distribution. I mean, multimodal, discrete, invariant, non-parametric. Okay, so that's the main idea of the talk today. So again, there are many approaches for this, and most of the approaches available in the literature will be the idea of symmetry in terms of a concept that is sometimes related to the idea of fitting, that is essentially you have a random variable that can be represented below as a fitted version of that random variable plus noise. And that idea has been used in the literature a lot. There is a very nice paper in 2001. It's a red paper in RCD, Bundles in Shepard, where we use this to construct a lot of modes for force. The theory goes very back into many papers in the 70s, in the 90s, in time series. And there's a very nice paper also with Harry Lowe for philosophy for for M series. So this is like the same idea as here, but the way you contract, the way you think, since they are discrete in most of these cases, it's not just by multiplication of a factor between 0 and 1 in this case. So these ideas of thinking are based on some default. But another idea is via stationarity, so you take a reversible process, and then you have this condition in the case of magnetic, you have the decay balance conditions. So if you have the decay balance conditions, you know that the process that you're going to converge is stationary. So what we do in MCMC is that we don't know the marginal, we don't know mu0 here, and we build up transitions to from the spaces in order to get to that. But here's the other way around. We know mu0. We know that we want to build this process with mu0, and what we want is a transition that keeps that process fixed. So this is not the MCMC, you provide to construct an model. Of course, with this condition, you get strict stationarity as well. So, in the same way, inner sequences can be used for this idea. So, take an exchangeable sequence, take two values of this infinite exchangeable sequence, and condition one with the other, and build up the one step predictive. And that, if you do it like this, is a well-defined market kernel. As simple as that. And then that's the idea that I'm going to use here. Okay, so I think it was yeah, whatever, and then take the one step ahead you want, or whichever, because it's symmetric. And you want to condition that defines a well-defined kernel, but this marginal the distribution of the table and variable. So this one here, for instance, this marginal the distribution that you use. So using this idea, there are many ways to construct this chain of tables to give you marginal distribution. I mean, we can come up with some ideas. This is an idea. You can define it through let's say that you have x given y and y, and to solve the transition is essentially the same kernel you have for the given sampler, x given y, y given x, and you construct the transition. So the same idea that you get the same kernel you get with the keys is the same kernel you get when you have two elements of exchangeable sequence and condition. Right? But I'm just using these because observations gives that very nice and quick way to do it. So the idea then is to construct these models, and the way to do it is to construct one step ahead predictive distributions that we know in the case of no parametric statistics, in the case of no parametric based on parametrics. So it's the expectation of the posterior distribution in one observation. So that is going to define them. So either these you do it parametrically or non-parametrically, there are ways to do it. And I will with some examples. Of course, there are many choices here. If you think about it, if you fix x, there are many x given y given x, many that is going to give you the same x, the same marginal. So parametrically speaking, you have many options, whereas no parametrically, the selection is really different. So this goes into the idea how to construct this how to do it. So you can propose a form of the posterior, provided you know that the x is mu0, and then determine via base the conditional probability of being x given y, and define the transition, or you can start the other way around, given x given y and y distribution, and obtain this. So you have the two components. You have it's how to build a length distribution with a given prescribed conditional distribution. That's it. You can do it the way you like it. We explore this way in control groups to make it non-tangible to develop a very small. So again, it's the same dependence as in this one. So I'll go quickly here because otherwise. So you have the discrete time, the n-step ahead transition probability is then in terms of these conditional distributions can be computed here. And in continuous time, which is the focus of this talk, you have to find which are the conditions. So Charles from the question to Charles define characteristic of the law of Markovian processes, the dynamics are present. So to do that, you need to see that the way to do that is to include in operating, if you are thinking in operating construction, to include a dependent Dirichlet process. It is the only way to do it. if you let it go all the way, you don't have this construction, you don't preserve this symmetry. So in this case, we are going to do this construction there. So an example is grow in that this problem involved is imagine you observe data, you take the histogram and the histogram looks like excluded tail distribution, and you want to build an algorithm because that excluded distribution is invariant. All right. So if you do that, then you can assume that x given y is a normal distribution, and immediately with base learning is conjugate, you have the whole model to complete the distribution. So in this case, the transition is also a student distribution, and it has this static equation which comes to a model of one set student of angle, generalizing that process. So it's a very simple idea, but the nice thing about this idea is that this model is immediately stationary and also reversible. Okay, so whereas the full version of OSF, you have like a general model to find the conditions, then to stationarity, and you have to work with it. If you start with this, you can immediately use this transition to build up the likelihood, to build up your model, estimate, to simulate the growth. So this is another example. You have a some distribution marginal, then you take one given subminal distribution, then you have the posterior distribution source concern, you take the transition distribution, which has its part of the form in terms of the elastic related function. But that model also can be written in this terms in terms of the linear representation with this equation here, which is essentially XP is given a binomial distribution with the total mass, with the n parameter x and probability psi plus an error. So it's thin, it's making it thinner, but in discrete time. So you are doing the same idea here. And this is again a very simple model. Again, you can use here the transition if you want to be always messy to estimate that. Or you can use the representation if you want to include the error. You will do this information, do a slice method or something. So the continuous version of that one is just to find so we include the only place where we can include the continuous time are C functions. So you need to find the C function of time that makes chemical reward equation to be satisfied. So if you do that and do the math, you will see that this is the solution. And that process that we saw before, when you continuous time responds to a graph, that was with the integration with this intensity function of that. So we know how to deal with these and class processes, but we didn't know about this transition, the simple solution. So, and we also have this plastic integration. Okay. So another example, and then if you do this, so is you take gamma, so you take say your observations of interest rate, you plot them and then you put the gamma, and then you say you want to construct a Markov process with this, but gamma is marginal. So you say, well, y in x is a Poisson distribution. Where the Poisson distribution has these parameters here, x with a particular function, and then you compute the posterior distribution, which is only with gamma, and we use two ingredients, you construct the transition distribution, which has this form. Then you solve, for example, the reward equation. Okay, and it gives you this form here. So immediately, if you block this back, this completely has an Markovian kernel to justify the construction. Now, to associate this to a particular model of interest, we know that so immediately you say, well, we have continuous time and continuous states. So the first thing is that is it a diffusion or is something that jumps, right? So to check that it's a diffusion, you check this condition that essentially tells you you cannot jump very fast in law. You cannot jump. It doesn't matter how far you go an epsilon, you cannot jump very fast. So this condition is called a linking condition in stochastic processes, and if this is satisfied, then the Markov process corresponds to the solution of stochastic differential equation with this mean function, this variance function, right? So in this case, particularly in the example we saw, we have this model here that is a well-known model for the Cox-Ingersoll-Ross model. So the Cox-Ingersoll-Ross models in finance is very basic for interest rates, and they do all kinds of tricks to estimate. But here you have the transition, and you know that this version of it is stationary. It doesn't matter how A and B are parameters they need. This process that varies to me. And this is the intensity of this version there. So you have a very nice little constructed, so essentially many I would say that most models that fall into the class of being the stochastic differential equations or diffusion processes corresponding to the solution of this equation in one dimension belong to this kind of constructions. there's a very nice paper on the essential touch of all of them are reversal, one condition. So there are many examples of this, and there are some papers with Steven and some students from visualizing the overlook this area. But what happened if we go to the what happened? So if you go this parametric way, you can construct many dependencies with a given marginal. So you have many microprocesses with the same marginal distributions, and that is not helpful at the time models. But you can do this well parametric and do the same again as I said before. Construct this in sort of nice way to construct these models, right? So have it predicted. But here it's still the marginals are going to be the marginals of the changeable sequence. So the marginal is still parametric. Okay, so this is the first bit for the construction. So if you take, for instance, let's say the Dirichlet process. You know, the one step behind predictive is the Dirichlet process is that in here. If you solve this, for example, world, allowing this parameter C to depend on time, you immediately realize that this is the solution of the process. So this kernel, this CFD included here, so the one step ahead, predictive of the Dirichlet process, is a very well-defined market process with this form here. It's called, in probability, it's called the Harris process. We know it more or less like it's related to science somehow, because you have a particular relationship here, and so it's completely dependent, or completely dependent in a particular way. That's what it's telling you more. So you have full independence just by one parameter. So it's a very nice process when we teach stochastic processes, because you can do pretty much like that. Everything we can with the generator and the mark probability is known as the mutation operator, right? That appears in many measured value processes. So many examples are used for this idea. So normalized processes use that in 2005 in a nice paper with Steven and all other research can use as well to construct this idea. But still, you have this parametric. So how to get stationary microprocesses with P invariant, say stationary processes with invariant distributions that add user, not necessarily just parametric modes, right? So when we do that in the statistics literature, of course, there is a literature on this in probability theory. Is we can use the same idea with here, like this model here. If you replace this space where this process is setting values by measures, the construction is still valid. So this is a nice way to construct with a particular rate. You take values from this process, and with the complement rate adds to one, you stay in that measure. So with the particular, it's the same idea that we had before. And that is also a very nice and easy way to construct a Dirichlet process that is Markovian. So let's go for the second part. The second part is quick because we have the talk in the morning, which is Peter is like, I have time, right? Plenty, right? So the same idea is as we saw this morning. So you use the hypothesis and then put the time dependency weights for the locations and see how this leads to a continuous time mode, in which way this can happen. So we saw that in particular where these are collections of stochastic processes in continuous time. So for instance, this VI can be a stochastic process that has a marginal distribution of that, right? So then it recover marginally the ways we would have in the Dirichlet process. So time dependence the ways for locations, and there are the choices, as I said. Following the stationary principle, so if the locations and are fixed over time, meaning you say you have an infinite locations, and the weights are going to tell you in which time you select which locations, because those the weights are going to be changing in time. So if you do that, then you preserve the same conditions you have in this stick or linear levels. Processes, if you have these are Napoleon reversible stationary, then you will have the same thing in the measured value process. So NP inherits the same properties and has an invariant distribution of these levels. But the problem there are continuity properties. We haven't spoken about those. So you preserve these low properties, but not continuity properties. So that's where I somehow was puzzled around, and then at some point There are other consequences you can take for correlations. Well, correlations, if you set the atoms are positive, you can allow to have zero correlation if you allow the locations to have complete connection. So the question we did, and Mateo was very, is like how to have a diffusion process that has invariant distribution is the process using this construction variable. So in that case, if you take this process to be a right feature, again, a process that has an invariant distribution of theta, 1 theta distribution, then this process is a stationary dependent diffusion process in continuous time. Okay? So that's a nice paper for knowledge. 2016. And that idea allows you to do mixtures of all of these things and estimate these kind of things that we see here, right? Like in this cartoon. So allows you to model even one trajectory and somehow multiple trajectory events. So another way to do it is instead of taking this V of the diffusion process, the Young process. This is the same Young process that I told you before. The same Harris process that I told you before, but written in a different sort of way. It's the same idea, and this is a simulation. You say we start a probability to the same state and jump into a different state. So if you use this with marginal beta distribution, you get again a different way to construct the model. And there is a measure program in a paper with Michel and Sarut. You can obtain correlations, and if you allow to have dependence on the locations, then you allow to recover when those dependent, when that dependence is zero, then you recover the autocorrelation of the measure value process zero. So this is the only way to actually recover that. I have 5 minutes, perfect. So that's the only way to do that. Okay. So these are the transition densities, the right feature case that I did with Mateo, and the other case that we've been exploring other cases that the distribution we already mentioned, right? So these are examples where the distribution stays on the same value. These are the data, and these are the estimations which we use. This is a place where we have no correlation, so each time you have different distribution. So essentially, we have also the estimation of the methods we apply, and this is a place where we have a jump. Okay, where we have a jump distribution. We go to a particular distribution, and then somehow we go to a bimodal distribution in a particular time, and the estimation also works in that case. The idea goes back to the paper I also did in Mateo and Steven 2011. When we use the same idea for the geometric process, which is a process, as you know, a random measure that even though it's full support, really it's not as free as the digital process, right? Sometimes. So then I have the last minutes to explain this idea. So you have a Markov process. The Markov process in homogeneous time somehow driven by a divide distribution, which includes the transition and the marginal distribution. So if you mix that, let's assume that this depends on parameters. If you mix that in a particular, not parametric mixture, you end up with this mixture here, and with this particular random mixture in a way that you have this kind of transition, a dependent, no parametric transition. Essentially, is telling you have the weights fixed on the point, and then you're going to jump to a particular distribution. It depends on a particular way you are mixing that distribution. So essentially, this is a well-defined mixture of Markov processes, but itself is not necessarily Markov, right? Because if you marginalize the whole thing, you lose the Markovity because you have several things. So in that case, if you do this, you can model the fix, and I'm gonna go quickly here. So for instance, if you replace that with one of Steve ideas, T-dependent processes, random probability measures, you end up with, again, using this idea of having dependent processes constructed, you end up like with a transition that depends on time as well. There is explicit dependence on time. And then this process can be extended in many ways. For instance, that process is a Markov process with this margin. So with marginals that are based on parametric mixtures. Enough time. So essentially, you can combine it into this, you can combine the same group here, which is a random same group, because we have random weights in the same group. And there's an example here that I end up with this example. Essentially, we take a gamma distribution, which is the one that we took before, the epoxy Ross process, and then we mix on that, we end up with a stochastic differential equation, which has a mean and diffusion, which are mixtures. infinite dimensions, right? Of these ways. So there are many ways to do. There is historian, what we have. So you can obtain the rates, right? I'm not gonna jump this. You have some nice cartoons that we all do at some point and see this. So extensions, we did an extension outside of the process, of course, we didn't have my paper with the Steven and this together here. And an idea that we are looking at, that we saw at some point, I think we can cover now, is to look at the functions. So what about the, you have one of these measure value process centered in a particular decision process that you like. And there is a very nice paper by Autónoma, Leo and Igor, where they are looking at the static way of studying means with a particular prescribed margin. So probably that will be helpful in this area that we were looking at. I will skip this. So there are some references. And thanks Steve for initiating such a nice and exciting thing. Thank you.
Thank you for creating a wonderful image. That's AI.
It was ChatGPT though. I just removed the background. The background was.
Any quick reaction? Otherwise, can we hold it for the end? We're running a little late. We started late. We're trying to move time. Then thank you for a big level talk. And it's the perfect introduction to the next talk because we're going to hear about the particular model by David Dunstan himself. David Dunstan from Duke University will talk about the logistic beta process.
Okay.
Because you started 5 minutes late.
Can you hear me? Okay, yeah. Is there how everyone acts like this thing doesn't work? Oh, it does work. Okay. Yeah, so this is largely a session in honor of Steve, and so maybe I'll just start out with a little bit of like historical background on how I got into this game, and then like Steve's inspiration on me, and then I'll go into these slides. And so yeah, I was sitting at Duke in a shared office. I was adjunct. I was worked at the National Institute of Health, and I was sharing an office with Codis. I guess he's right here. And I had a revision at JASA where I was fitting some Bayesian model to count data, and the referees were complaining that it was only flexible in the mean. And I was like, well, maybe I can play with one of these Dirichlet process things. Seems complicated. And I remember asking Codis, like, how complicated is it? And he's like, oh, it's not that bad. And so then I just like put it in there. And then that was when I started working on Bayesian nonparametrics. And then I just sort of really got into it. And I was really inspired by Steve's Dependent Dirichlet Process paper, not necessarily because it was a dependent Dirichlet process, but I think the key idea there really was taking that, like before you'd have like a Dirichlet process and then you could put lots of flexibility and stuff. But here you were like actually taking that random measure and allowing it to vary with stuff according to a stochastic process. And that to me like opened up a lot of modeling ideas that I got really excited about with density regression, kernel stick breaking, logistic stick breaking, everything else. And I think a lot of other people as well. It's sort of like a light bulb opened up, and it allowed us to kind of have some creativity in building like an amazing class of different models. And so I think that was a lot of fun for the community. And then Steve, I think, really had one of the first pivotal kind of change point papers that opened up that field, well beyond the Dirichlet process setting. And I've really enjoyed also interacting with him over the years. He often sits there and he has these really kind of insightful comments. He's very deep intellectually and really asks thought-provoking comments that are surprising. And so I've enjoyed that as well. And I find this quite fun because, you know, often I was like, oh, I do this boring Dirichlet process. Let's do something else. Let's put in some sort of, you know, other process that's not a Dirichlet process. And so one of the punchlines here is that we have this paper that Cheng Wu Li, who's a postdoc with me, is first author on, in which we sort of like define a new class of Dirichlet processes which ends up beating like one of my favorite models that we came up with, which was the logistic stick breaking process, and which is actually a former dependent Dirichlet process, unlike our model. Okay, so I'll get to it. So this is joint work with really two fantastic young people, and then also Hoyan Sung is also fantastic. And so Cheng Wu Lee is the first author in the paper. He's a postdoc with me. He'll be on the academic job market. So anyone who's looking for great faculty, he's a really delightful guy, great communicator, has a lot of ideas, very independent. Also, Ali Zito, who was a recent PhD student of mine, who's now a postdoc at Harvard. He's also fantastic and will be on the academic job market. Okay, so this is the team. And so I would say I would like to also give a little bit of a big picture motivation, because I think in our community we work on all these cool models and we develop all these kind of probabilistic properties, and you have the Milan Italian school working on the kind of probabilistic properties of urns and things, and then the kind of Subhashis Gosal, Odd van der Vaart type working on asymptotics. And I would like to give a little bit of a call to the community to come up with more practical models, and maybe an R package for fitting these damn things. And so we could actually be using these more in practice, and then expand the community out a bit more in that direction. So we're not, the applications aren't like writing like a JASA apps paper, but we're actually doing it in real applications in a scientific journal, things like that. So I would say there really remains a need for easy to implement flexible, computationally efficient, robust approaches. And this is one reason the applications of our models really lag far behind the theory and the fun of building the models. We build the models and then almost never, nobody actually uses them in real applications. And I think that as a community, we want to move down that gap. Okay. And so we try to, maybe it's like a little baby step towards that goal here, just to try to become more computationally tractable in defining dependent Dirichlet processes. And more broadly, I would say the key technical advance is that we have this logistic beta process where we can put dependence in multivariate beta distributions or beta stochastic processes. Beta distributions are one of the key building blocks of a lot of BNP models, including dependent Dirichlet processes. Okay, well, yeah, so we use the beta distribution all the time in Bayesian nonparametrics. Obviously, you all know what the beta density looks like, or you would have been very lost in all the other talks. Okay, so the Dirichlet process uses the beta and the stick breaking ratios. We can go beyond the Dirichlet process to the Pittman-Yor process, and we still have a beta stick breaking representation. The polyetry, Lee Moss here, who's has really done amazing work on building on and extending, developing new models that are related to polyetries, also uses betas. The Indian buffet process, which is something we just started working on kind of recently. Federico Camerlinghi's here. Him and his students and colleagues and other people have been doing amazing work extending the Indian buffet process and developing a new theory, which is really, really beautiful for these kind of latent feature models where you have not a kind of a regular mixture model, but you have these binary latent features. And so, famously, the Di-Fumnetti measure of the Indian buffet process is the beta process. And so the betas also come in these type of latent binary feature models. Okay. So betas are coming in a lot of places and are key to the kind of analytic and computational tractability of a lot of the Bayesian nonparametric models. Okay, and so we've seen this a gajillion times at this point, but this is just the stick breaking construction of the dependent Dirichlet process, or just the Dirichlet process initially. And so this is just, oh, well, of course, we can write our random measure, maybe underlying a mixture model if we're using a density estimation approach, and as a kind of infinite discrete distribution with a bunch of atoms, and then we have these stick breaking weights. Everyone in here has seen this because it's in the previous talks. And then the dependent Dirichlet process, of course, we put in little x there. So that could be time or space or covariates or whatever. And then we could have potentially the stick breaking links, and also the atoms depend on the covariates. Okay, and then if it's a dependent Dirichlet process, you have g of x is still marginally following a dp. A lot of the fun crap we've messed around with over the years is like, oh, well, why make it a beta? Like maybe it'd be convenient to just write these down as some sort of generalized linear models or something, and we could have a binary response generalized linear model. And then if we used a probit, that would be a probit stick breaking process. If we used a logistic regression, that would be a logistic stick breaking process. And it might be pretty hard to study some of the properties of that. That was the argument for these normalized random measures, but it's really convenient computationally and quite tractable in a lot of problems. And so those have been quite popular. Okay, so so another thing that was mentioned in Steve's famous GSM Proceedings paper, which is hilarious. I love this, like, because we often like look at like where these papers appeared and everything, and then there's a lot of fundamentally good ideas that are like terminal archive papers now. But, okay, so and this kind of builds on the original kind of motivation of Ferguson for like what we would like to have for a Bayesian nonparametric model. It kind of extends that. And so for a dependent BNP model, what would you want? You would want large support. Felipe had a really great talk about talking about support properties of the DDP. We want to have tractable computation. And so we would, as I mentioned, we'd like to be applying these in all sorts of applications. And so how can we make computation really as easy as possible? And ideally, we could just like throw different applications at it and have it be automatic, even fold it in something like Stan or probabilistic programming language, or maybe one of these. Now they have these Python packages, which are really promising in terms of routinely implementing Bayesian models that we started using, like NumPyro. Okay, the marginal, we might want to like have some sort of feel for what the marginal is doing. That's a lack of some of the models we developed in the past, because otherwise we put this stochastic process on if we have no idea what it's doing marginally, and there might be some sort of drift systematically over the X space that might create a little bit of artifacts that you don't like, and I'll show some results on that later. And then unless we have some reason to think that we want some jumps or something, we probably would like to have continuity. Okay. Okay, so if we want all of these things, you know, one of the forms of the marginal that is really well studied and understood is the Dirichlet process marginal. If we have a, you know, G of X is maybe a mixing measure in a kernel model for the actual data, then we might want to maintain the Dirichlet process property. And if we use the stick breaking representation, then we want to maintain beta 1 alpha marginal weights. Okay, and so some of the models we've worked on previously and other people have worked on previously, kind of largely driven by the fact that we want something that's computationally convenient, including, you know, the probit stick breaking process paper, the original one in JASA. We were trying to do variable selection in the context of density regression. You have a lot of variables. You want to like allow them come in and out through something like a spike slab prior. That might be hard if we used a Dirichlet process that allowed the weights to vary and hence the kind of clustering structure to vary. But if you put it in a probit, it's pretty easy, or also it'd be easy with a logistic. And so that was a nice property of those, but then we kind of sacrificed the marginal property, and that can have some consequences, as I will show later. Okay, so so satisfying the computation of beta marginal is a challenging task. There was a really nice description by Felipe earlier of the copula approach. And so one obvious thing is like, okay, well, I want beta 1 alpha marginals, and now I have some sort of X dependence. It could be space or time or predictors. And so now I could define some sort of copula model, maybe Gaussian copula, or multivariate Gaussian, or a Gaussian process copula, or some other copula. And now I want to maintain the beta marginals. Okay, so you could definitely do that and define all sorts of models. And there's a whole series of nice papers on that approach. Felipe's paper, Alan Gelfand did a bunch of work of that type for spatial processes with various students and postdocs. But really, the copula approach, computation becomes pretty challenging, I think. And we would like to have something that is easier to implement in general than conceptually you can write down a model, but we would like to be able to do easy computation that doesn't cost too much per iteration and overall. There's also some really nice work. I really like this paper by Lorenzo Trippa. He had this really clever formulation that I quite liked, using kind of shared gamma random variables to induce dependence while maintaining a marginal Dirichlet process property. And there's also been some quite a bit of other work as well, including by a number of people in this audience. Okay, but maybe sometimes in a narrow setting, still in an important setting. Okay, so what the heck do we do? Well, we introduced this logistic beta process, A to X, whose logistic transform leads to a stochastic process with common beta marginals. It's quite flexible in terms of like allowing a broad class of dependent structures. You can allow discrete continuous X, you could have temporal, you could have spatial, etc. You can allow a wide range of strengths of dependence, perfectly positive to negative, and you can get pretty efficient posterior computation as well. Partly building on a lot of the beautiful things that have been done for logistic regression models by Nick Polson and others in terms of these polar gamma data augmentation. We can play related games here as well for this logistic beta process. Okay. So the logistic beta process you could use as well in other contexts, like putting in covariate dependence in Indian buffets and things like that. But here we're honoring Steve's DDP, so we'll focus on the a logistic beta use in doing dependent Dirichlet process modeling, particularly in density regression. Okay, so what the heck is this logistic beta creature? So we'll just focus initially on the logistic beta, a multivariate case instead of the univariate case, just for time. And so let's say we have eta, which is n variate random variable. It's drawn from a logistic beta distribution parameterized by an A, B, and a correlation matrix R. How do I get that? Well, we could draw the etas conditionally on a lambda just from a multivariate normal distribution. So this is getting really simple. And then it's like 0.5 times lambda A minus B, a one vector, and the covariance of the normal is lambda times R. Okay, and R is just like a correlation matrix. And then the lambda is drawn from a Polya distribution with parameters A and B. Okay. And then since R has unit diagonal, it turns out that each component of eta marginally follows a logistic beta density, which could just be written down in the simple form that I won't show here. And then the logistic transformation gives a multivariate beta distribution, and then the Polya turns into a beta, Polya AB turns into beta AB marginals. Okay. And then you have this really nice multivariate beta distribution that with a data augmentation scheme can be very convenient computationally because we have this Gaussian there, and also we can have a multivariate beta of marginals of AB, and we have this correlation matrix R controlling dependence. So I think it's quite a clever formulation that really Chang Wu came up with. Okay, and so we can kind of plot some density plots of this, and so the top is the density of eta drawn from a logistic beta just in the bivariate case for just let's set A equals 2 and B equals 4, and then we can choose R, and then we can see that we can get like a variety of dependence, and the bottom is like after we apply that logistic transformation, and then now we're back to the 0-1 support. Okay, so we can like get different degrees of dependence. It could be very positive or it could be negatively dependent, etc. Okay, so what else can we say about this multivariate logistic beta? The covariance has this form, and so if A equals B, those are the two parameters in the marginal beta. If A equals B, we just have the covariance between A to I and A to J is just this simple multiple of the correlation, the R. It's not the marginal correlation, but it's like a correlation matrix that induces correlation marginally between the I and J element of that correlation matrix. Or it's a little bit more complicated if A is not equal to B, because that's a more flexible case. And here these psis are just di and tri gamma functions. Okay, so if A and B is equal to B, it's symmetric and the correlation has full range. If it's asymmetric, it does have a restricted range, but this is sort of like a inevitable consequence of the asymmetric marginal by nice work of Joe in 2006. Okay, he's worked a lot on copula models. Yeah, we don't have a closed form, but we can easily just sample. You just draw Monte Carlo samples, and then you can get an estimate of the correlation after applying the logistic transform between those kind of marginally distributed beta random variables. Okay, so that's the multivariate case. You know, in a lot of models, we'd like to define a stochastic process instead. You have a continuous model over a covariate space or with space or time. And so here we can define, instead of correlation matrix, we can define a correlation kernel, which is mapping from this cross product space to -1 to 1. So like the diagonal elements are just 1, and then we could define whatever kernel we want, and we have lots to choose from the literature. For example, on Gaussian processes, we could choose the covariance kernels that are used in those contexts and just plug them in here, and kind of go to town and building all sorts of fun spatial, temporal, et cetera, processes. Yeah, so the logistic transform of eta has a beta AB marginals. One example is we could do a discrete time model. We have a density that's evolving over time, a discrete time, you know, where it changes in flexible ways across time, and we could do that. But now we can put in some sort of, let's just say, some sort simple row parameters controlling how much the dependence falls off over time. Okay, in terms of the distance between the discrete time indices. Yeah, and then we could do it also on a continuous domain, and we could do like a Matern kernel, so we could do quite flexible classes of processes. Quite straightforward. Okay, so then we have this logistic beta building block, which is very flexible. And since we want to make Steve happy, we're going to put it within a dependent Dirichlet process. How does that work? So okay, well, here's our measure valued stochastic process at value x. It just looks like the usual dependent Dirichlet process. So we have, these are the stick breaking links, but now we're making them be the logistic transform. So this is marginally beta distributed, where this thing is drawn from the logistic process, the logistic beta process. And yeah, and so we just do that for the stick links, and then we could do whatever we want for the atoms. And so these etas are just like IID from a logistic beta process. And now we have that A and B. If we want it to be marginally Dirichlet process, if we wanted it to be a marginally a Pittman-York process, we could choose different values. But here we want it marginally to be a Dirichlet process, so we choose 1 alpha. And then we have this correlation matrix, including inducing dependence across the X space in these in the stick breaking random variables. Okay. So yeah, so it ends up being pretty straightforward. Now we can, what do we do? This is the mixing measure. Now we can just put it in the a density regression model. Let's just say we have univariate response y, and we have a bunch of predictors. So now we want a model for the density of y given x. And now this is just a mixture, say, of Gaussian kernels with variance varying across the components. And now we could let the means vary flexibly, potentially with some sort of mean regression model. We could use splines or some type of kernels or Gaussian processes, whatever we want. And then we also have the weights now on the different kernels are also varying with covariates, and that's driven by this logistic beta process. Okay, so that's like a nice density regression model that's going to be, you know, it's kind of nice marginal behavior, and it's also very easy to implement computationally. So we can kind of go back to Steve's Desiderata for BNP models. So does it have large support? Yes, it has large support. And this was mentioned in Felipe's really nice talk. He cited our paper and mentioned this. The computation, yeah, we'll discuss that soon, but we can just do a very simple kind of Gibbs sampler, data augmentation Gibbs sampler, at least for most of the parameters. And marginal, it's just a Dirichlet process or Dirichlet process mixture for the marginal prior for f of y given x for given x. And yeah, we have flexible, we have continuity, smoothness across the g of x. And the correlation is going to go to 1 as x goes to x prime. Yeah, it's all nice how it falls out. Okay, so what about computation? So for computation, like the thing that I guess I come from a biostatistics background, and I've seen a lot of these discrete survival time models. And so as soon as I saw the stick breaking ratios in the Dirichlet process, I was like, oh, we could just like, that's just basically a discrete event time model. And now we can put in covariates, we can put in whatever. And then, okay, well, how do I do computation? I can just do data augmentation with some binary indicators of whether I died or not at each time. And then now I can just do whatever, you know, Albert and Chib or Polya Gamma data augmentation, depending on whether I had a logistic or probit. And then I'm good. Now everything's a simple GIF sampling. So we're going to run a similar Ponzi scheme here, where we sort of define these stick breaking links, and then we do this kind of continuation ratio GLM trick where we augment with these binary latent variables for whether you died or not at each time. And then you can kind of just update all of these conjugately, and then you have a bunch of regression models that are going to be conjugate after data augmentation. So what's the overall scheme? And so for each sample, we just update the component allocation. So which mixture component did you get allocated to? Then we update some Polya Gamma random variables, stealing Nick Poulsen and colleagues' wonderful tricks for logistic regression. We can update the Polya mixing parameter, which we can even allow to vary across components. And then the other parameters are just from the multivariate normal. And we can then update our component-specific parameters however we would, even like it could just be conjugate of the kernel as in a normal mixture model. Okay, and so this is really, really simple, kind of similar to the logistic stick breaking process. Tommy's here. They have this really nice paper with Tommy and Daniele in 2021 on kind of efficient computation for logistic stick breaking processes. But a key difference is that we maintain this marginal DP behavior, whereas the logistic stick breaking might do strange things as we vary over X. It's not well understood, as Antonio Leoy was saying, that one reason they really like these normalized random measures is you can like really study the analytic properties a lot cleaner than in the stick breaking case. Okay, so I'll just show some simulation study results to try to show some of the advantages. And so we just study, we have this latent logistic beta model for binary data, or we have a Gaussian copula-based model. And so we just considered two different data generating models. So we could generate from a Gaussian copula, or we could generate from a logistic latent logistic beta model. Okay. And then we could say, okay, well, if we generate from the Gaussian copula and then we fit our logistic stick breaking mixture model, then maybe we fall off a little bit relative to the copula-based model, but maybe we don't. We can see what happens. Okay. Yeah, and so we consider different values of dependence across space. It could be predictors, and yeah, we use Stan for fitting the Gaussian copula model because there didn't seem to be any generally available nice code, and so we just put that into Stan, which worked fine. Okay, so what do we get? So in general, we see that just to say the kind of bottom line is that it's massively more efficient to do the logistic beta process. I would say that even if we had some efficient code for the Gaussian copula computation is much more unwieldy. So it's kind of more difficult to get to work. And we also have a lot of block updates. So we can like just put all this stuff in some multivariate Gaussian distribution due to the form of the logistic beta after data augmentation. And that helps the mixing as well. And so we get like massively higher effective sample size per second for our sampler relative to the Gaussian copula. And then when the Gaussian copula is the true model, we do very comparably in terms of actual predictive performance. So that it's sort of a win-win. Okay. And this is just the same kind of deal. It just shows also some sort of errors that we get in terms of density estimation. Here we're estimating a density that can vary with predictors, and we could look at the L1 error, and we could look at the RMSE, and we just show box plots. Here we also throw in the linear DDP. Maria and Steve, that was the first published version of the DDP. It was a really beautiful model, but somewhat restrictive because you have a fixed weight, so you don't allow those to depend on covariates, and then you're kind of mixing linear regressions, and so that can kind of fall off if that structure doesn't hold. And so we get some big advantages relative to the linear DDP in terms of errors. And we tend to do a little bit better or similarly to or better than the logistic stick breaking in each case. And what we noticed is that the logistic stick breaking is really less sensitive to hyperparameters, and that's due to the fact that we've kind of tied down the marginal at each point. Whereas if we take a logistic stick breaking, there can be systematic variation in the prior variance and various things across the predictors. And I'll illustrate that with this pregnancy outcome data example, and then we'll be done and hopefully have a minute for questions. Okay, so this is the data example I used a lot over the years to illustrate density regression, because the gestational age of delivery, it tends to be like the right tail is like tied down because the baby can't get too big or has to come out. But the left tail, that corresponds to preterm deliveries. And so you tend to get this kind of left skewed distribution that doesn't look very Gaussian. And also the left tail can change with covariance. So if you get some nasty environmental exposure, then you get more preterm deliveries. It doesn't shift the right tail of the distribution, just shifts the left tail. And so it's a really nice kind of example for density regression that's been used in our kernel stick breaking paper and through a series of papers over the years. And so we used it here as well. We can just put it on a personal laptop. It runs in less than 10 minutes for like way more than enough iterations. And here's sort of one of the bottom lines. And so this is the estimated probability of preterm birth with a 95% credible interval for smokers, so women who smoke during pregnancy, under 3 different hyperparameter settings. And so it's for the L to L, our proposed model, and the logistic stick breaking model on the bottom. And so we can see as we change the hyperparameter settings, we get the same result where the probability of preterm birth is kind of going up with the exposure, but the interval is about the same. I'm out of time, okay. But now the intervals change a lot with the logistic stick breaking across the hyperparameter values. And so one of the robustness is one of the big advantages. And I'll just stop there because we're out of time.
While we are preparing for the next speaker, any quick reactions? Please see. Very nice talk. I noticed that the thing this scale mixture because we seem to open up flexibility on how the models are. And in your talk, you seem to be using a pretty simple kind of kernel. But I suppose you can generalize this to like the class, like
yeah, that's a fantastic suggestion. Yeah, that would be wonderful. Yeah, you could put on all sorts of rich structure. Like there's been a lot of interest in these kind of graph structured dependent Dirichlet processes. Because you have a multivariate Gaussian, you can like kind of fold in, updating schemes modularly into that. Yeah, that's a great idea. Yeah, thanks, Lee.
Thank you. So let's thank David again. Thank you for the nice talk. The values on the so let's just move on. And actually, it's perfect. Next talk is Mara from MIT. And after we've seen the big picture, then like a specific example, now we're kind of back to thinking about how to do things into context, I think. Please, Tamara. Tamara, we tell us about the DDP and local exchangeability.
Okay, great. There we go. Great, awesome. Thank you so much for being here. This is a really amazing workshop. Thanks for writing these original amazing papers, Steve. So today we've seen so much super cool work already building on Steve's dependent Dirichlet process. I'd like to take in a perspective that I hope is complementary to Ramses and Antonio's talks. And in particular, think about a lot of this work as relaxing a strict exchangeability assumption and instead exhibiting something that we might call local exchangeability. Before I go on, I want to highlight that the paper that I'll be talking about today that is not the DDP paper is a paper where Trevor Campbell is the first author, did amazing work, also with amazing collaborators as well. Okay, so as I said, we're thinking about going beyond exchangeability. I find it super helpful to have a concrete example in mind. And so as my concrete example today, let's imagine that I have a bunch of articles, maybe they're about sports, and I'm trying to cluster them. And so I've got all my articles, I'm going to try to set them, into mutually exclusive, mutually exhaustive groups, clusters, and maybe I'm trying to find out what those clusters are about as well. And so when I examine them, or as part of my algorithm, I realize, oh, actually, a bunch of these articles are about football, a bunch of the articles are about baseball, a bunch of the articles are about basketball, et cetera. Now, if I was trying to figure out, these relationships of articles to each other, probably if I'm at today's workshop, I was thinking, man, I'm going to take a Bayesian approach. And so what's going to be involved with that? I'm going to be choosing a set of priors and a set of likelihoods. One of the things I'm probably going to need to choose is a prior on the frequencies of the clusters. So I might be thinking, hey, I'm going to use a Dirichlet process on the cluster frequency. And of course, an issue that's come up a bunch already is that, yes, the Dirichlet process has all kinds of super amazing qualities. It's super flexible. It has all these nice computational properties. It lets us have an unbounded prior on the number of clusters. But the straightforward application of it to something like clustering would be stationary in time. And of course, we know that that's not realistic. For instance, in this concrete example, the reality is, I guess back in the 50s, baseball was the most popular sport in the United States. And of course, that's changed today. Nowadays, football, American football, is the most popular sport. Also, you get all these random weird sports that you didn't hear about sort of, maybe some decades ago. Like nowadays, people run 200 miles in one go, and that's totally a sport that a number of people are involved with. And so it'd be nice, of course, to have something that, really allows this kind of change over time. And as we've heard about a ton today, of course, the dependent Dirichlet process is something that we could integrate into our generative models that we could use to model this and actually learn these kinds of changes with covariates more generally, not just time. And so what I'd really like to do today is treat the Dirichlet process and the dependent Dirichlet process as examples of different types of regularity that we can use to learn from data. And we always need some kind of regularity to learn from data. This is a point that came up in Ramses' talk. And these are just different types. And so for instance, in the Dirichlet process, that regularity is exchangeability. If I saw my data points in a different order, maybe I think it shouldn't matter. Or particularly, in this example, maybe I just downloaded my articles from Wikipedia. I think the order I downloaded them in shouldn't matter. It shouldn't change the distribution of the data. And so in that case, I'm going to assume my data is exchangeable. Now, if I assume my data is exchangeable, much broader than the Dirichlet process, I get all kinds of really nice things. Like I get Dependencies theorem as a representation theorem, which has been used to justify likelihoods, priors, Bayesian inference, in fact, Bayesian nonparametrics. I get consistent estimation. I can actually estimate the things that I care about. I get permutation tests and hypothesis testing and all kinds of other super nice things. And so with the dependent Dirichlet process, we've actually heard this in a couple of talks already, the regularity in many ways was designed to come from smoothness in the covariates. Maybe I think that articles about sports that are in adjacent weeks aren't exactly exchangeable, but they're pretty darn close to exchangeable when they're close in time. And so I feel like there's still some type of regularity there that I should be able to use for inference purposes. And the question then becomes, can we formalize that type of regularity? And can we have all the nice things that we expect from exchangeability, but now for that type of regularity? And to that purpose, we define local exchangeability, and can't really tell, but we show lots of analogous benefits under that text there. Okay, so that's what we're going to talk about today, defining local exchangeability and talking about some of those benefits. And so in the remainder of the talk today, I'm going to start by expanding on this example of exchangeable clusters and expanding on this example of time-varying clusters with the dependent Dirichlet process. I'm going to use those examples to motivate our definition of local exchangeability, our representation theorem for local exchangeability, again, analogous to Dependencies theorem in the exact exchangeability case, and then talk about some of these benefits that we get from taking a local exchangeable approach. Okay, so let's dig in on this example, just expanding on the example that I already started on a bit earlier. So remember, we're taking a Bayesian model for clusters, and so we have to be choosing our priors and choosing our likelihoods. The first thing that's going to come up, or one of the first things that's going to come up in building this Bayesian model is, we got to choose some prior on the cluster frequency. So that'll be some set of values that are between 0 and 1 and add up to 1. You know, maybe let's suppose for the moment that I have 5 clusters, and so I'll have a bunch of intervals that span 0 to 1. And I drew these at random, you know, this is just a random draw. Okay, so now I got to choose my assignments of data points to clusters. And basically the way that we're going to do that, the typical way, is equivalent to, hey, for every data point, I'm going to draw uniformly at random an IID uniform random variable. These are all going to be independent of each other across the data points, and also independent of these intervals that I already drew. And so for the first data point, it's always going to form the first cluster. And when 2 of these IID uniform random variables fall into the same interval, they belong to the same cluster. So here, when I drew the next IID uniform random variable for my second data point, it belongs with the first data point, and they form a cluster. Maybe I draw the third data point, it forms a new cluster. I draw my IID uniform random variable for the fourth data point, it forms a new cluster. Data point 5 belongs with 3, 6 forms a new cluster, and 7 belongs with 1 and 2. And so now I have my cluster assignments. It's just the data points that go together form clusters. Now, typically, if I'm building up my full Bayesian generative model, I don't stop here. I draw some identities for the clusters. Maybe these are parameters that represent that they're about different sports themes for these articles. And finally, I draw the actual data points, conditional on the identities in the cluster. So the actual, you know, what are the actual words that are in the articles? Now, of course, that would be the full generative model. Today, I'm going to focus on this part of the generative model that I've described here. Okay, well, gosh, I don't probably know that I have exactly 5 clusters. Certainly, if I'm thinking about sports, I would find it hard to name all of the sports that exist. And so I might choose, instead of having just 5 clusters and some prior over that, to put a Dirichlet process prior over the cluster frequencies. This will let me not state a bound on the number of clusters, but conversely, I'll now have a countable infinity of clusters here. I find it hard to draw a countable infinity, so I put a little dot, dot, dot there. You can imagine there's a countable infinity of these frequencies. They get smaller and smaller. We get rarer and rarer sports. And there'll always be that countable infinity all the time. Okay. So hopefully something that's pretty straightforward, especially from this cartoon, to see is that this must generate an exchangeable cluster assignment. In particular, if I'm changing the order of the data points, all I'm doing is changing a bunch of these IID uniform random variables. That's clearly not going to change the distribution of the clustering. They were all IID uniform to begin with. And so the clustering must be exchangeable. Now, the cool thing is that in 1978, Kingman showed the converse was true. If I have any exchangeable clustering, that is to say, I just know I can exchange the order of my data points and get the same distribution over the clustering, it must be that the distribution of that clustering is equivalent to, first, I draw randomly these cluster frequencies. Maybe there's a countable infinity, maybe it's finite. And then I make these IID uniform draws to assign data points to clusters. And so this is just a particular representation of Di-Finetti's theorem, a particular representation theorem for exchangeable clustering. It's super cool on its own, but it also gives us a lot of implications that are really useful. One particular implication is, well, let's imagine that I'm using this in my generative model to draw assignments to data points to clusters in this example of sports article. Well, if I'm drawing assignments of data points to articles, of data points to clusters in these articles, no matter what time I'm doing it, I'm always drawing from the same cluster frequency. So if I'm drawing articles, oh, and DP, the DP gives one particular paint bound. Okay, so if I'm drawing articles in January, I have the same cluster frequencies. If I'm drawing articles in March, I have the same cluster frequencies. If I'm drawing articles in May, and any time of year, I'm going to have the same cluster frequencies. Okay, well, if you have a passing familiarity with sports in the United States, at least, you know there are seasons to sports. There are some kinds of years where people are very actively talking about baseball because all the big parts of baseball are going on, all the big games, same thing with football and so on. And so actually, it would be much more realistic to think that the frequency that people are talking about each sport really varies across time of year. And that's something that we see that not only can we not get with the Dirichlet process, but because of the Kingman paint box theorem, we see that we can't possibly get that with any exchangeable process. We really need to get beyond exchangeability to capture this kind of behavior. And so what can we do? Well, again, we've talked about the dependent Dirichlet process so much today that will allow these cluster frequencies to vary over time. Of course, it will also allow the cluster frequencies to vary over other covariates. For instance, I expect that in Colorado, they talk about skiing a lot more than they do in Florida. And the cluster identities. So certainly the people who are involved in football today are very different than the people who were involved in it in, say, 1960. And so we expect these to vary over time as well. And we can capture all of these things with the dependent Dirichlet process. Now, just having the ability to change things over time isn't enough on its own. If I have a totally different set of cluster frequencies and identities every nanosecond of the year, there's no way to learn across, to learn what's going on from my data. This is a point that came up again in Ramses' talk as well. And so really I need some kind of regularity to really learn when I'm allowing this variation in covariates. And this is exactly, I think, the ethos of condition 4 that we just saw in David Dunson's talk, in MacEachern's original 99 and 2000 papers, that we essentially need this smoothness condition to be able to learn. And in these papers, it takes the form of a continuity across the covariates. Okay, so we have this cool idea of exchangeability that lets us have these representation theorems and lets us say really broad things about what we can and can't do in clustering. And now we have this sort of idea of, what we'd like to do to get beyond exchangeability is have some kind of smoothness in covariates. And we have an equivalent notion of regularity, a formalized notion of regularity as what we have for exchangeability. And can we have representation theorems to go with that? And so that's where we're going to come in and define what we're calling local exchangeability. Now, before we define it, let me just introduce a little bit of notation. First, we're going to let X be our stochastic process, and we're going to let it be indexed by a covariate T. So in the running example that I've had, you can think of X as being the assignment of the article that's at time T to a cluster, in particular, in this case, to a sport. Well, we're probably going to see a whole bunch of articles that are written at different times. So let's collect all those times in capital T, a collection of covariates. When we're working with exchangeability, we're thinking about taking the order of the data points, X1, X2, X3, X4, and permuting the indices of those data points. In local exchangeability, we're going to be thinking about taking these covariates, the times articles were written, and changing those just a little bit. Like what happens if I just had an article written at a slightly different time? And so pi is going to be the map that takes us from a particular time or covariate to another one. It'll be injective, that is to say, if I start from two different covariates, I end up at two different covariates. And then finally, we're going to want to compare the stochastic process at a particular set of times, xt, to the stochastic process where we just change those times a little bit. So x, pi, comma, capital T will be, hey, let's take the times in T, or the covariates, change them a little bit according to pi, and then look at x at those times. Okay, so here's the rough definition of local exchangeability. For all the supermeasure theoretic details, check out our paper. But the rough idea is, we're going to say that the process X is locally exchangeable if it's close to exchangeable when the covariates are close. Okay, we're going to have to fill in a little bit of detail here. First, what does it mean for the covariates to be close? Well, it depends on what you're trying to do. We're talking about sports articles changing over time. Maybe closeness should be something like Euclidean distance in time. If we're thinking about a process where we're interested in periodic behavior, maybe we want closeness in like month of the year, modulo of the year. The point is you're going to have to choose a D, a distance D. So once you've chosen your distance D for the covariates to be close, we'll say that we're locally exchangeable with respect to D. Turns out you only need a pre-metric, not all of the elements of a metric. And then second, so now I've said what it means for the covariates to be close. Now I want to say what it means to be close to exchangeable. So in particular, what's essentially happening here is saying if D between when my articles were written and let's say the next day, so very close by covariates, if that's very small, then the total variation distance between the distribution over my original set of articles written the next day, should be very small. These should be very close distribution. If on the other hand, I'm looking at articles written in 2025 and articles written in 1960, well, all bets are off. Those are really far covariates. And so there's pretty much no implication on the line itself. Okay, so maybe to help us wrap our minds around what's going on here, let's just note that in some sense this can be seen as an extension of just straight exchangeability, regular exchangeability. In particular, if we think of the covariates as just being usual natural number indices like x1, x2, x3, x4, and I permute any of those covariates, that is, I just change any of them, and my distance is 0, so I'm not allowing this false 0, this has got to be true. I'm saying this is exchangeability. That's just exchangeability. A common form of partial exchangeability is exchangeability under invariances. So we could have a situation, or under just certain groups. So we could have a situation where, let's say I have a subreddit that's about basketball and all of the articles in there. And I have a subreddit that's about baseball and all of the articles in there. And so maybe I feel like the articles over here could be exchangeable within each other. The articles over here could be exchangeable within each other, but not across the groups. So that would again be a special case where we just let the covariates, the indices 1, 2, 3, 4, etc., and we say that the distance is 0 within these equivalence classes and 1 if you're across. That is, you can just do anything if you're across. Okay, but again, that's sort of the power of this, or where we really think, you know, we're excited about this, that this goes beyond things, is that we let things be smooth. In cases where we really have this sort of non-trivial distance, something like a Euclidean distance, that you can change very smoothly away from exact exchangeability to just being a little bit off from that, which is, I think, what we expect in, for instance, this motivating example. Okay, so we've defined local exchangeability, but again, our question is, you know, what do we get out of that? And let's first start by asking, do we get any kind of representation theorem, like for exact exchangeability? So in order to think about this, it'll help to just revisit what do we actually get out of exact exchangeability. What's definity? Well, definity says if I have my exchangeable sequence X, so X1, X2, X3, X4, that'll be exchangeable if and only if there's a unique random measure G such that the X's are IID conditional on G. You can think of G as being those frequencies of the clusters in our example earlier, and X as being the assignments of data points to clusters, for instance, in that original Dirichlet process model. Man, there's a lot of work on representation theorems for exact invariances. I talked earlier about the Kingman paintbox work. We've done work on extending that to feature allocations, where each data point can belong to one and only one, or sorry, can belong to multiple groups instead of one and only one group. Like I could have an article that's about multiple sports. We can go to trait allocations. People have looked at arrays and networks. We've done some work in this area, Markov chains, so on, tons of work. We think, though, that this is the first representation theorem for an approximate probabilistic symmetry. And so here's again the rough version of the theorem. We're going to say that the process X is locally exchangeable, again, with respect to D. You got to choose a D, a distance in the covariates, if and only if. Much like for exchangeability, we're going to have this unique G that underlies things. The difference now is that G can change with time. So just like in the example, we had that the cluster frequencies were always fixed in exchangeability. Now, GT is the cluster frequencies at a particular time t. And then we're going to get two things. Unlike exchangeability, where we had one equation up top, we're going to have two equations. So the first is that now, instead of conditional IIDX, we have conditional independent X. And in particular, we have GT as sort of that conditional measure for the teeth element of the covariates. And then two, we get that if the covariates are close in this B that we define, then GT has to be close to GT prime. Again, thinking of this something like, in a very rough sense, at least in this expectation sense, that, you know, if I have two times right next to each other, like I'm looking at one day and the next day, I don't think that the proportion of people talking about football is changing that much. Okay, so again, exact exchangeability and this partial exchangeability over these equivalence classes for special cases. For exact exchangeability, remember D is equal to 0. So we're saying essentially the GTs are always equal to a particular thing, let's call it G. And so then all of these are the same G, we're getting out exactly the same. And a similar thing is happening for partial exchangeability with equivalence classes. Okay, so we've got our definition of local exchangeability. We've got our representation theorem. What kind of benefits can we get out of it? Again, let's come back to exchangeability and think about what's going on with exchangeability. Well, we're trying to, at the end of the day, we'd like to estimate something like G. You know, again, there's frequencies of the different clusters. And so we're going to estimate it. Let's call this thing we're estimating G hat. It's going to depend on the number of data points, our estimator. And if we were trying to estimate the frequencies with which each cluster occurred, probably the most natural thing would be to say, hey, from the data I have so far, let's just take the fraction of articles that occurred in each cluster. That's a really natural estimator. And one can show that as n, the number of data points, goes to infinity, that this G hat n converges weakly to G almost surely. So dP here is the Levy-Prokhorov metric. We have that extra almost surely because G itself is random. Okay, so what can we do in local exchangeability? We're going to take a very similar weighted sum approach, but just adjust the weights a little bit. Okay, so again, we're trying to estimate G, but as we said before, now G depends on a covariate. So really we want to do something like estimate G at a particular covariate, let's call it tau, where we're aiming to make the estimation. So we're trying to find the cluster frequencies, the frequencies of articles about different sports at this particular time tau. Now, instead of just n data points, it matters where our data points are. There are particular covariates. Let's collect those in capital D or capital T. And we're going to have a weighted sum with some slightly non-trivial weights now. And let me describe at a high level what's going on with these weights. So first, if I'm trying to estimate the cluster frequencies of articles about sports, March 1st, 2025, I probably don't care too much about an article from 1960. That's not telling me too much information. And so the weight on that article from a really, really far away time is going to be 0. 2, I'm not just going to take an empirical average of values that are close to my target covariate, because there's some bias. None of them are exactly on that target covariate, and depending on how far they are, I have different amounts of bias. And so we're going to incorporate that bias in our weights. I'm not writing out the formula here just because it's a lot of extra notation you can find in the paper, but it's totally tractable. It's totally closed form. It doesn't involve anything, even in like MCMC or variational Bayes. It's just a straightforward weighting sum. Okay. So then let's look at what can we do with this. We can estimate the process locally like we could for exchangeability. Now, in exchangeability, just up ahead, we had n, the number of data points going to infinity. We have to be a little bit more careful now. If I have an infinite number of data points, articles from 1960, and again, I'm trying to estimate something going on in 2025, that doesn't really help me too much. I don't actually think I should be able to estimate the frequencies in 2025 very well. And so we can't just have an infinite number of data points now. We need the number of data points near our target covariate to become infinite. If we do that, then we get G hat T tau does converge weakly to G tau in probability. We also get that this approximates the posterior predictive. What do I mean by posterior predictive? I mean the distribution over X, over our stochastic process with a particular tau, given the observations of X at all the observed covariates. And so basically we can show that the same G hat T tau becomes a better and better approximation of this posterior predictive as we get enough data points near that tau. Okay, so let's bring it all back to the dependent Dirichlet process. We show that the dependent Dirichlet process is in fact locally exchangeable. Technically, we do this for a wide subset of dependent Dirichlet processes, but I suspect that basically everything is locally exchangeable. The corollary is that for sufficiently smooth variation in the DDP, the local empirical measure process, this phi hat tau, approximates the top period predictive. Just to be clear, I mean essentially the cluster assignments in that example that I was giving before. Two, technically speaking, this is always an approximation. It's just a good approximation if this is sufficiently smooth. Again, you've got to have some data that's near in this D sense of your covariates, the true data, to get a good approximation. I haven't talked about other nice things. I'll just mention them really briefly. We get other nice things with local exchangeability. We can analyze permutation tests with covariates. We can deal with bin or rounded covariates. They don't have to be exactly our particular covariate observation. And so on and so forth. I'll encourage you to check out the paper if you're interested in that. Okay, so let me just go ahead and wrap up and say a few final things. So first, today I talked about local exchangeability, introducing local exchangeability. And exchangeability is we swap data and got exactly the same distribution. And local exchangeability, we're swapping data at nearby covariates and getting a bounded change in the distribution. We provided a representation theorem analogous to Dependent's theorem for local exchangeability and practical estimators, among some other nice things. The dependent Dirichlet process provides one locally exchangeable process, but I want to say it's actually quite a bit more than that. Arguably, it's sort of like a canonical locally exchangeable process. I think, we've really seen today that it's formed the vanguard of just an incredible collection of locally exchangeable processes. And of course, not just in clustering. I mean, the original papers were about regression, but it's just inspired so much work well beyond that, including our own. Of course, check out the amazing papers by Steve. Like Jim, I went back and reread them, before this talk, and I think they really stand up incredibly well. Like, what an amazing set of papers to read. I'll also say, much like many other people have discussed, I think Steve himself has just been an incredible inspiration. My first ever conference was not a Bayesian conference, and it was a horrible experience. I didn't know anybody. I didn't meet anybody. I hated it. Then I went to the BNP in Veracruz. Incredible experience. And it was really Steve and people like Steve, who I think just makes this community so incredible, so supportive. It's the kind of thing that really makes me want to keep working in this community, to be a part of this community. And it's just been really incredible. So I want to say a big thank you for that. If you're interested in checking out the other work that I talked about today, you can check it out in this Bernoulli 2023 paper. Again, first author is Tremper Campbell on local exchangeability. And then finally, I'll just mention, I think that like these general ideas are not even specific to Bayesian modeling and inference. Something that we do as Bayesians, but also frequentists do, and just everybody does, machine learning, is we use things like cross-validation for evaluation. Well, if I look at a fold of cross-validation, I'm taking an empirical average of a loss over the validation data point. That is justified as an evaluation because it estimates test risk. That is justified as an estimator of test risk by an exchangeability or IID assumption. If I'm working in a temporal or spatial process, that assumption breaks down. And I can show, or we show in this paper, that basically you can misidentify one model being better than another, when in fact it's the other way around. And so we really need evaluation methods that are able to handle things beyond an IID or exchangeability assumption. We also look at this in terms of uncertainty quantification for associations in a follow-up paper. Okay, I think I'm at time, so thank you very much. Thanks again, Steve. Really appreciate it.
Thank you for a great talk, and good try to do more talks. Any quick reaction before Steve gets to make his comments in life? Then Steve, the floor is yours for some final comments.
Is this one? Yes.
Wow. All I can say is, first off, thanks to all of you guys for showing up. It's just.
Just use this one.
Here you go. I'm technologically challenged, as everyone who knows. Challenged in many, many ways. I thought, before hearing all these very, very kind talks, that I would try to talk just a little bit about some historical issues and just talk about the wonderful, wonderful community that is BNP, and some of it tied to dependent Dirichlet processes, but primarily just BNP. And for me, a lot goes back to just early days of BNP. And I worked on BNP in my dissertation back in the 1980s. Don Barry was my advisor. Very, very committed Bayesian, very subjective Bayesian in many ways. And of course, had a huge impact on the world, primarily through his work on medical testing, medical trials, but also on building an incredible group down at the MD Anderson Cancer Center that was just strong for so many years before there were structural changes that if you go back early days of BNP, right, back to Ferguson's paper, read it. It's an extraordinary paper, and some of those other early ones as well. People picked off all the problems that were accessible, and they simply had solved the problems that you could solve with the technology of the time in the 1970s, early 80s, things like that. And things just sort of didn't quite die out because there were a few people that really kept things alive. And certainly Don Barry was one of them. If you look at it, he had a string of students in Minnesota that he got involved in Bayesian nonparametrics, myself included. And of course, it carried over to other people who were not Don students, but were someone like Michael Levine, did polio trees, created those, and things moved on there. What really took some time, though, was to establish a community. And when you had no problems to work on, there couldn't be a community to form because you couldn't have a conference, you couldn't have gatherings. You'd have, half a dozen people in the world who were working on Bayesian nonparametrics, but very, very small number. And of course, it was after that really there started to be a community that would form and would establish itself. And, there were growing pains at the beginning, as you would expect anytime a community is formed. And, I speak of that not because growing pains are bad, it's just what happens anytime that there's not a community yet formed. And, early days there were, troubles with refereeing, long review times. I know there's a paper of mine that took about 18 months to get reviewed. That's in the Communications and Statistics that prides itself on fast review. And the big comment was I should redraw a figure with greater resolution, which was a good comment because, in 18 months, technology had changed and the graphics had become better. So fine comment, but, disturbingly long wait. But once the community started, it really began to establish itself. And if you look around the room, you can see the incredible people. Many have been part of the community for many, many years. Others who are sort of newer. For some, I presume, this is the first gathering of BNP that they're really showing up at. It's an extraordinary group of people. And one of the fun things for me is I actually had a fun when I kind of grew up. Just being around remarkable people. And I'm one out of 6 kids and, I had a couple of parents. And if I look at it, all of the others are just smarter and brighter than I am at some fundamental level. And so, I'm not terribly intimidated when I'm around people who are just smarter and brighter and more creative than I am. And when I look around the room, I see a lot of this, right? Alessandra mentioned it at the webinar that, when she first showed up at a BNP meeting, she really found it was an extraordinary batch of people. And I think that's still very, very true today. I just look around and we heard the talks today. We read the papers that we see in the journals, and one after another, they're just blockbuster papers that are really remarkable. And I think that's part of why BNP has grown so much and become so specific. Part of it too is just that it's, you know, it's an incredibly open and welcoming group of people. And I think that's in part tied to who the people are. You know, dynamic people, interested in truth, want to pursue the ideas and find out what's real, as opposed to just write another paper and things like that. You know, it's that spirit that is just open and welcoming. 25 years ago, there wasn't very much of machine learning that kind of cross-pollinated statistics anywhere. And BNP has been one of the big touch points, where there's been wonderful energy that came in from machine learning, I guess AI now, that really helped grow the field of Bayesian parametrics, grow statistics, and I think some was fed back into machine learning as well. So a lot of it's just community, but it's really the people, and same people show up again and again because conferences are fun, and it's just a wonderful crowd of people. Dependent Dirichlet processes, you know, I'll just kind of skip over because we heard wonderful descriptions of those today, and far better descriptions than I could ever give of the technology and the many uses and variations on things as well. For BNP, just a couple of things, right? Going forward, BNP is never going to disappear. Right? It's a big thriving community. I've heard it's 300 who are signed up for this conference, which is truly a remarkable thing. I was just at the OBASE meeting over in Athens, and that was about 100. There's also the BaseConf meeting, which was in Singapore. I didn't get a count on that, but there was a big number of people there as well. These meetings are going to proceed forever, right? And the community is simply going to grow. Why does it grow? Well, in part, you know, the models are closer to reality. And anytime you have models that get you closer to reality for modeling data, you get better predictions, you get more understanding. They simply work better. And if you can fit them in compute and you can use them, they're not going to go back. We're never going to go back to simpler models when we have better technology available. And so, you know, I think that the community is only going to grow. Venice, the big ISBA meeting last year, you know, I asked a few people, you know, what fraction of talks are based on parametrics? And it's not just the distributional things, but things that are sort of wiggly mean functions, whether it's bars or whether it's Gaussian processes. And there were variation in the estimates, you know, that I heard. But I think most were more than half the talks had an element of Bayesian parametrics. And when you see that at kind of the ISBA World meeting, you know that it's just, you know, it's taken root in the community. And I think everybody learns a little bit of Bayesian parametrics if they learn Bayesian now. Some people learn a lot, but it's just fundamentally present. You know, a million other things that I could, you know, go on and on and on and talk about. But what I wanted to say is that this notion of building community is just huge. And, you know, something that I think is often not appreciated when people start out in academics. I mean, you get a start, you go to a few conferences, you're writing your papers, you're trying to survive. And yet, to be part of a good, open, welcoming community makes an enormous difference in how people feel when they're doing the work. And I think Bayesian non-parametric community is the best that I've ever seen, quite frankly. All of science, all of statistics and things like that. It really is an amazing group. And you see that from all the speakers today, but also you'll see it in the rest of the week as the conference. What I'd like to do is call out the attention to two things that I think are communities that are waiting to really completely form. And the start has already begun on these communities. But when I look at it, they could easily be the size of the Bayesian non-parametric community if you go forward 20 years, 30 years. And so think about these and you know, pay attention. First one is going to be the workshop this afternoon on predictive methods. I mean, those really are big, and we saw a connection with some of the talks today. You know, those methods are in some sense tied to exchangeability, but in ways that are not, I think, entirely clear right now. But that's all going to shake up going forward. So, you know, the predictive methods and how you build models, how you use those, how you use them for practical problems, as David called that. What can these models really do for us, not only in the world of statistics, but across science? And that is just waiting to happen. Some of those models have a very clear advantage is computation for speed, which is a big issue and a real issue. And that will be a welcome contribution in the future. But that's one community that's just waiting to be formed. Second one, I think I would call it robustness, but model misspecification, handling outliers. There are a million versions of robustness or lack of robustness that are around. Bayesians, I think, are not as good as we should be about handling model misspecification. Some other communities are actually quite good at it. They just do local averages and smoothing, and it actually turns out quite well. But that's one that I think is again, a community that has a bit of energy and starting, but a lot more can happen. And just called out, two or three things that are there. Generalized Bayesian, of course, is a big approach on the robustness issue. Bayesian restricted likelihood that I will. And also just plain writing down Bayes models, BNP, that has huge support, and then dealing with things with inference after the fact, rather than as part of the modeling, seems to be an effective strategy. I have students who are working on each of these. For the top one, you could check out Tori Hilbert's poster that'll be at the poster session. And the robustness one, comparing generalized Bayes and Bayes restricted likelihood. Shinyu Zhang will have a poster as well. So go visit them, talk to them at the poster sessions. I think they're. But for these again, put a little effort into building community. I mean, the communities will take off if conferences start to be organized and there's really sort of a kernel that leads to growth. But these two are just naturals in my opinion. And I hope that both of them take off in a big, big way. Last little bit. Oh my goodness. Thanks to all of you guys, especially to Michele and Alejandro for taking and organizing such a touching and for me at least kind of wonderful, wonderful day. It's really, really very, very special. And I'll say not only for me, but I tell my parents about it, and then they like it too. That's always a huge thing for all of us, of course. The speakers, well, wonderful talks, right? And not just wonderful talks, but talks about wonderful work and whole streams of work. We actually see the energy that just runs throughout really the whole community, the vibrancy of the community. And of course, it's not just the speakers, but the whole BNP community. And so thanks to everybody who's here. Thanks also to the people who could not make it here today. And I was tempted to say that this is really a kind of a once in a lifetime event. In some ways it is, but then I thought about it a little bit more. And there's this tie into the Eastern religions where people talk about sort of rebirth, regeneration, and things like that. And this is more like a once in a several lifetimes event. And I discovered some, I gotta tell you, with Maria's wonderful photos. And if you notice, it turns out that both Wes and I are wearing our pajamas today. With that, I will say thank you very much, and I look forward to this afternoon's events. Thank you.